Object-Orientated Programming in Python, OOP. What is object orientation? Object orientation is thinking about data structures as objects. What do we mean by objects? Just a special kind of data structure. The full answer is more nuanced, but I want to examine the answer with increasing detail. What problem or problems does object orientation solve? What are the alternatives and how does programming work before object orientation? There are many questions that need answering to perfectly define what object orientation is. Let us continue our naive definition with what is orientation. That is easier to answer than what is an object, which, as a programmer, you will be asking yourself in every programming challenge you tackle. Orientation is focus or prioritization. In object orientation, the object, data structure, receives our attention. This is sometimes referred to as bottom-up programming. We're building units of functionality, library units, objects, which the next programmer will reuse. Reuse is a core concept in software engineering. Never reinvent the wheel unless your boss asks you to. Not invented here syndrome, NIH. Reuse is not exclusive to OOP. Python likes to remind us of the distinction between dry, don't repeat yourself, and wet, write everything twice. Reusing code means less new code needs inspecting, understanding, and crucially, though outside of the scope of this video, testing. Now we may consider what came before OOP, less abstraction, and more thinking like a machine. Machine code is just numbers, and no one can read it. Humans write, or at least they used to write, in assembler. Assembler maps mnemonics like add, ADD, SHL, shift left, LODSB, load string byte into register, to these numbers. On top of assembler came another language, BASIC. BASIC is the first language I learnt at school in the 80s or 90s. BASIC fits into the narrative here because it bears, at least in the form I learnt it, an important resemblance to machine code, line numbers. Machine code has been called imperative. Imperative is the far end of the spectrum of sequenced instructions. I have seen Python scripts where people just lazily copy and paste function bodies into code instead of calling the function. I've also seen that in C++, but I'm primarily a Python guy. These programmers will still be in post before and after me, so I cannot say that imperative programming is intrinsically bad. Its advantages include not needing to scroll or jump around the code. IDEs have largely removed that problem, but too many jumps or jumping within the same file makes it easy to lose your place. I would not consider imperative programming to be anti-OOP. They can and will exist in different parts of a program. I'll bring it up, and it is often brought up as an alternative to OOP, because sequential programming, whether OOP or not, is a cornerstone on which all languages are built. On the other hand, imperative is often used to contrast with declarative. Declarative isn't much used in business logic, but is suited to making front ends that don't hold state. This is a second sense of the word imperative. Objects typically do use imperative programming in their implementation, and objects may also appear in declarative layouts. Widget X, text box Y are both full objects. New objects may also be declared in markup, like XML, as consisting of other objects. Proper four-pillar object-oriented programming in a declarative language would be seen as an anti-pattern. Abstracted away from machine code and assembler, C translates more readable code into assembler, or machine code. Converting C into assembler is relatively straightforward if the machine vocabulary is limited, RISC versus CISC, that's reduced instruction set versus complex instruction set. An old CPU will be relatively simple. With decades of programming language evolution out of the way, we can consider how object orientation solved a problem that C could not. Before objects, we only had data structures, which C conveniently calls structs. In order to see the benefits of OOP, our example will consider the data structure lifeform. I want this to be the most generic way of describing any life form in a fantasy world. We might use it for orcs, humans, wraiths, other undead, or even plants. Every life form has a measure of vitality, or life remaining, which by convention is called HP for hit points. In C, we don't have objects, we have the direct ancestor, the struct. Here I've created the lifeform struct with HP and max HP members, or fields. In OOP, we call variables within an object members, member variables, or in the case of Python, attributes. Here in C, they are simply members, because variables are the only type of member a struct may have. Movement speed is never used, but illustrates the purpose of creating a generic base type. The function main is the entry point where execution begins by convention. I create a variable of type lifeform and print its attributes. We can forget about C now. If I hadn't studied it at uni, I'd probably never have used it subsequently. The problem with structs is their members are limited to variables only. They can contain no functions. Having the data structure define its own functions is core to OOP, as we'll see later. This leads to another alternative to OOP, that is procedural programming. Again, this is not really an alternative, as all programs require procedures to a certain extent. What OOP does is make the data structures, now called objects, own the procedures. This is the first of 4 pillars in OOP. Encapsulation. Here in the C++ version, the default access is private. If only the constructor is public, then the client cannot access the member variables to output. The compiler, or the IDE, gives an error when we attempt to do so. It's worth considering this very minimal piece of C++ in more detail. These access modifiers simply don't exist in C, and for compatibility likely never will. Encapsulation means restricting access to certain data. Access controls are not intended for security. Even friendly clients may be assumed to abuse them. It is a common misconception to consider encapsulation suitable for sensitive data. What then is the point of encapsulation? It is the private protected side of public interfaces. Good, i.e. supported, clients can rely only on the public interfaces. The other side of the coin of access modifiers is another of the 4 tenets of OOP, abstraction. Abstraction is exposing only the necessary details to clients. There's a reason access modifiers are private by default in C++. Encapsulation refers to the private implementation, while abstraction refers to the public interface. Best not to dwell on these 2 pillars too long. C++ does them quite well, and is certainly harder to circumvent than Python, as we will eventually get to. The remaining pillars are more obviously distinct. Inheritance means making subclasses from, and these are all synonyms, parent, super, or base classes. The child class inherits all members from its parent. This helps promote code reuse and leads to hierarchies of classifications, including the dreaded diamond pattern in C++. We aren't considering C++ here, and we'll see that Python, with version 3.0 only being released in 2008, has learned from its forebears in its implementation of OOP. Polymorphism means many forms. Here we have take damage with 2 forms. A normal life form will take all the damage, but a warrior only takes half damage. Which version gets called depends on the type of the object. With the theory out of the way, let us move on to applying it to Python. Python is famously, but not uniquely, duck-typed. When a function is passed an object, it does not, usually, care for the class of that object. Instead, if it expects a duck and it quacks like a duck, then it is a duck. But what is class in programming? A class is the template from which new objects are created or instantiated. Remember that an object is a data structure with functions or behaviors like quack. Python adopts the we're all consenting adults approach to object orientation. It does not enforce access modifiers like statically typed languages do. Instead, we have naming conventions of prefixing an underscore or 2 underscores to represent protected and private access modifiers respectively. In fact, Python refers to members protected like this as internal use since PEP 8. As we shall see, internal probably refers to module level here rather than class level. This is a rare example of where encapsulation is distinct from abstraction. We can from X import asterisk and know that internal use members are not part of that import. Private members start with 2 underscores and their names are mangled better than protected members. It certainly won't be perfect protection. Internal use appears only suited to encapsulation of namespaces being imported wholesale, which is considered bad practice as it can lead to name collisions and namespace pollution. This refactoring of encounters to their own module is a brilliant example of polymorphism, because the encounters module knows nothing about any subclasses of lifeform. It expects a lifeform, along with the interface defined on it, and just calls one of its methods. Whether that method is linked to the original implementation or an inherited one, it doesn't care. You see, I can easily access the internal use strength member of the warrior class. When I make it private, I don't easily recall how I should access it.